I'm Liz Rice. This is the eBPF and Cilium Office Hours, episode 140. As always, do say hello, type in the comments, let us know where you're watching from, and I hope you're going to have lots of questions for us today. We're going to have a really interesting dive into some networking performance improvements in eBPF and consequently in Cilium. But before we get to that, let me just run through a few items of news and housekeeping. So there's a couple of very, very relevant events coming up. We have the eBPF Summit. It's going to be on the 11th of September, online as always. So mark that in your calendars now. And if you have an idea for a talk for eBPF Summit, we'd love to hear about it. If you go to the eBPF Summit site, you'll find the link to the call for proposals, and you have until 17th of July to get those ideas into us. Also, we're looking for people to help us review those talk proposals. So I've added a link in the show notes, which is that side, I think, on HackMD. So if you find that HackMD show notes for episode 140, you will find that link to the program committee application, and you can help us choose the talks and the program for eBPF summits. All right, a few people are saying hello. We've got Joseph saying hello from Paris, hi, and Nico, who's also French but from Manchester. So yeah, a lot of folks from France, that's great. And Joseph does say the best people are here. Excellent. All right, the other event that's coming up this autumn is the Cilium and eBPF Day co-located event that takes place just ahead of KubeCon in Salt Lake City on the 12th of November. There is a call for proposals open right now for that as well. The deadline for that is just 3 days ahead of the eBPF Summit deadline, so 14th of July. So that's all about Cilium and eBPF, particularly in a cloud-native context, given that it's a CNCF event. Okay, hello to Tony. Great to see you, Tony, regular viewer, awesome. Right. Couple of blog posts that caught my attention. I found both of these in the newsletter that Bill Mulligan puts together every couple of weeks. This was just two of the highlights from the latest edition. So one of those is about how the Tetragon agent gets information about process lifecycle events through eBPF maps. That is by Yuki Nakamura. Very nice Kubernetes and Fuji logo there. I really like it. And I think this is a really nice walkthrough of a real life example of getting information out of an eBPF map and doing something useful with it. It's also part of a series about how Tetragon works and investigating how Tetragon's put together. So really nice series there. The other blog post that I wanted to highlight, I think might be of interest to folks who are diving into eBPF, is this one about using BPF programs and TC to redirect DNS traffic. Again, it's a really nice kind of walkthrough. It's got, if I scroll down enough, well, it's got diagrams of what's going on. And I think if I go down far enough, we'll start seeing some code. Yes, we do actually see some program for how that TC attached program can work. Great to see a few more people saying hello. So we have Ganitak, hi. We have Mariusz from Poland, great. And we have Andy. So thank you so much, all of you, for joining. I think it's now time to also have join us our guest for today, who is my friend and colleague, Daniel Borkmann, who is, you know, one of the co-creators of eBPF. So there's no better person to have talking about the internals of eBPF. But today we're going to particularly concentrate on some enhancements that Daniel and others have been working on to improve networking performance through something called netkit devices. So hi, Daniel, welcome.
Hi, Liz. Thanks for having me.
Always have your expertise here. So yeah. Oh, we have another hello to bring on. So hi to Gassan. Awesome. So tell us, what is a netkit device?
So that's a new device drive and a new device type in the Linux kernel that we developed. And the idea is to replace Weave devices and then have netkit devices as the connection points of pods with the outside world. Why?
So just to fill in for people who might not know, so Weave devices are virtual Ethernet connections.
Yeah.
And in a containerized environment, that's how we connect the host namespace to the container's network namespace.
Yeah, exactly. And why did we want to do that? So why did we want to rethink how pod networking is being done? Well, the idea is simple. Like we wanted to have as low overhead as possible, so that basically when you deploy applications, they would have the same performance characteristics as if they would be deployed in the host itself. And here it's the case. We wanted to have the same performance in terms of throughput and latency when they are in pods. So basically, no overhead for pods and network namespaces essentially. So this was our big goal for the work that actually lasted like 1 to 2 years.
Nice.
Quite a while.
So how did the idea come about, and who's been involved in it?
I would say it started maybe many years ago. Cilium, like in one of the really old versions, it had support for IP VLAN. And back then I added support for that. We got it to some degree working, that you had basic connectivity. But then like we noticed that there are like a lot of drawbacks because of the IP VLAN internal architecture, that it wouldn't work well for Cilium itself. I mean, it works well for other use cases, but for us, where we wanted to attach BPF for various different reasons, like policy enforcement, load balancing, and whatnot. So the way we basically approached this back then was that Cilium attached the BPF programs. Maybe I should start with how IP VLAN works. That's probably the best way.
Okay.
So in case of IP VLAN, you have a physical device like your ETH0 in the host that you connect to the outside world. And that would be, you would set this as your IP VLAN master device. And then you can, on top of that, link IP VLAN slave devices to that. And they would basically be put into a pod or into a container. And IP VLAN has an internal routing table. And the idea there is to basically move traffic in and out quickly. But it has like a lot of limitations when we want to attach BPF to it. So the way we did this back then was basically to attach the BPF to the IP VLAN slave device inside the pod. But there are problems that attached with this, because applications could actually unload that. That's like the first drawback. And the other drawback is it's really hard to implement routing, and L7 forwarding and other things, because they are in the host namespace, like inside the host. And if you attach something into the pod, it doesn't have access to this. It doesn't have this context. It doesn't know how to route it there. And on top of that, I mean, yeah, so there was like a number of problems. Like one of the other one is in our BPF programs that we attach in Cilium, we basically match on the source IP addresses, and if it's something else that the IPAM for Cilium has been configuring, then we drop the traffic in order to avoid spoofing, for example.
Okay. Yeah.
And with IP VLAN, that's, if you really wanted to do that, you would have to do this in the host namespace, so that some bad actor cannot do whatever they want inside the pod and unload the program. But there it's impossible to know because you really don't know where the traffic actually came from, the way how IP VLAN works internally. So yeah, there were many problems, and in the end, we removed support for IP VLAN from Cilium because up until now, the main way how Cilium operates is basically with Weave devices, those virtual Ethernet devices, and there we can solve all these problems. Because a Weave device usually has two legs, one leg inside the pod in the network namespace and the other one inside the host. And then what Cilium does is it attaches the program inside the host namespace, because with that we can do all these things, like we can do policy enforcement and forward traffic to L7 load balancer, do encryption and whatnot.
Right. And it's outside of the reach of the application.
Exactly.
Space.
Exactly. However, it's like Weave devices, they have their drawbacks in terms of performance. And that's basically how this whole journey started, looking into how can we optimize and make it better. And with Weave devices, you can imagine it as follows. So if there's traffic outside the node going into a pod, in the worst case, you have two feedback loops. One is the traffic arrives on the physical NIC. Then we have the forwarding logic in eBPF. It forwards it to the Weave device that is inside the host. And then the packet is basically being enqueued to a so-called per CPU backlog queue. And if the system is under pressure, if there's lots of traffic going in and out that needs to be processed and whatnot, then it can defer, in the really worst case, work to process that backlog to a kernel soft IRQ daemon. And then that kernel soft IRQ daemon picks up the packet and pushes it into the input path of the kernel so that it goes up the network stack into a socket in the application. So you have...
So this is like there's too many incoming packets or they're coming in too fast. Yeah. So this software IRQ is essentially deferring it to be handled a little bit later.
Yeah. And so with that, you basically have the switch from a transmit to a receive path, right? Like from the host side, you transmit it to a Weave device, and then inside the pod you receive it. So it's like the switch. And given Weave devices, they were designed back then when also the kernel stack was smaller than it is today. There was the fear that, well, if we don't defer it, the worst case that could happen if you process it, if you process something that way, it could be like a kernel stack overflow. If there are too many pieces involved, and so it's better to have like a different thread and starting from fresh.
Okay.
So you have this double feedback loop, and the goal was basically to completely get rid of this. Because with BPF, we do have all the context that is needed in order to forward the packet. And the idea with netkit devices was basically to get the best of both worlds, right? Get the best of IP VLAN in terms of performance, but also get the best of the flexibility that Weave devices had in terms of BPF handling. So we basically designed netkit devices in the kernel, especially for Cilium's use case.
Right. So actually, that makes me wonder, are there other ways of using netkit other than by having BPF programs attached to them?
Yeah, of course. I mean, you can use it as a replacement for Weave as well. So I wanted to have it also operate even if you don't want to attach BPF to it. So that's definitely possible to connect network namespaces to that as a drop-in replacement. And there are some benefits to this. If you think about Weave devices, so Weave devices, virtual Ethernet, so that's basically L2, right? So why do you have to handle ARP resolution and things like that if it's just like connecting something from a network namespace to the host, or it's not really needed. So the idea was also to have this actually configurable. So with netkit devices, you can have an option. By default, it is an L3 device, but you also have the option to configure it as an L2 device in case you want to do some network simulation with routing and whatnot. But like the default operation is L3, and L3 basically means when a pod sends traffic to the outside of its pod, then the neighboring subsystem of the Linux kernel does not try to resolve MAC addresses, for example.
Okay.
So in that case, the source and destination MACs, they will all be 0. And it doesn't have to do any of this work because the host itself will do it anyway later on when it wants to send the packet outside of the node. So so it eases up some aspects. For example, in Cilium, we have this fake ARP responder in BPF to basically act as a next hop to get traffic out of the pod, and those things are not needed anymore. So it makes things simpler, and also inside the kernel, some of the data structures, like for example for the next hops, they don't have to be they don't have to have this churn, this extra churn, so you can save those resources as well. So and basically the overall goal was like getting back to the double feedback loop, to get rid of it and to have the BPF programs that we attach in Cilium today inside the host weave device on the TC ingress. So they handle the logical egress traffic when traffic goes out of a pod. Basically have those programs, and we attach them inside the pod, inside that netkit device. So that's what we call the netkit peer device. So there's also a primary and a peer device. The primary device is inside the host namespace. It's orchestrated by Cilium. And the peer device basically holds our BPF LXC BPF programs. And no application inside the pod can change or remove it and whatnot, right? So that's not accessible.
Is that like sort of special casing? Because presumably it is inside the application's namespace.
Yeah, that's correct. So it's basically attached to the driver for that netkit device, and that netkit device sits in the pod. But it's not manageable from the pod itself. You can only manage those programs from the primary device.
Okay.
And the primary device is the one that Cilium has access to.
Right.
And with that, what is then basically possible? So that the outgoing packet goes to the netkit device inside the pod. We immediately run our BPF programs, and shortly before we do that, we switch the packet's device pointer to the one of the host device. And that is basically implicitly like a switch of a network namespace.
Cool. Right. Yeah.
So this goes really fast, and then the BPF program, if the BPF program sees and does a kernel fib lookup, and it sees, okay, like now it needs to go out, like out of the node to some location in the internet or some other Kubernetes node, then we have this context. So we can do this lookup because the lookup is based on the network namespace. The network namespace has already been switched to the one in the host. And once the packet returns and it says, okay, please forward it to this physical device, we forward it directly through BPF. So we basically inject the packet into the neighboring subsystem of the host namespace. And because of that, the host namespace, like the stack from the host namespace, will then populate the MAC addresses and whatnot, and then it will send it out of the physical device. So you don't have this per CPU backlog queue. You can do this immediately. And the same thing happens for packets going into the pod, right? So there's packet arrives on the physical device. We have BPF attached on all the physical devices. And we know that the packet is local, like destined at this pod. Then we can redirect it as well with the special helper that we developed some time ago. It's called redirect peer, and it's also doing the same trick, right? So it's basically resetting the packet's device pointers and doing another loop through the main receive path of the network stack. And with that,
so that when in that BPF receive peer helper function name, that the peer is the netkit peer.
Yeah. So yeah, exactly. So basically, you redirect it to the netkit in the host namespace, but it will then fetch the pointer, the device pointer that is inside the pod, and it will reset them into kernel and do another loop. So it's also instant, right? So it's not like you have to encure it somewhere again, and then worst case under pressure, kernel software IQ daemon picks it up and whatnot. So like that is mitigated with that, because you can wake up the application immediately.
Amazing.
And with that, you basically.
Sorry, did you have some diagrams of this?
Yeah, of course. Let me see if I can find it. I think you would have to put the.
Shall I bring it on?
Lights on the screen.
There we go.
Wait. It's not yet the one. I think this one. This one, yeah. So that's basically an overview of the architecture and all the building blocks that we built over the years. And what you can see here is basically the host itself, Kubernetes worker node, and then there's the pod. And instead of going to the upper stack, where you have the kernel forwarding layer, where you have netfilter and various other things, you can directly forward the packet to the network card, which then pushes it out of the node. And the same for the input path. And the BPF program is sitting on the netkit peer device, so inside the pod, but inaccessible from the pod. So I think that's probably like a high-level overview. And yeah, in addition to netkit, we also developed in general a new TC BPF data path layer to make it faster as one aspect, and then also to have a better API and BPF link support. Maybe I should elaborate on this as well a bit.
Yeah, that's the TCX thing, right? There's
TCX and netkit. So like those were the two bigger projects that we've worked on last year in the kernel, and now like with Cilium 1.16, this has been fully integrated and can be used. So yeah, like TCX. So basically, that's like it's called TC Express. So unlike XTP, like a little bit like that, but I think like the TC data path is super critical and super important in general. For Cilium, it's like the foundation, it's like the building block, and also for various other software outside of Cilium. And given it operates on SKBs in the kernel, it is just very critical. And the issue that one of our users ran into longer time ago, before TCX was there, was that with the old style TC BPF, some users like BPF software was stepping onto each other's toes. Like one was unloading the other by accident. So this was like really tricky to find bug when we were thinking, well, like everything looked fine except where's the BPF program attached, and like no traffic was going, and there was also no concrete error. So what is happening, right? And we saw that
multiple programs attaching to the same point.
Exactly, like to the same TC BPF point, basically, that you can find like in the host namespace in the Weave device. And okay, so we actually in BPF, we have a solution for that, which is called BPF links. So BPF links, they hold the reference to the BPF program, and you can attach them to different points, and then the application has to manage that link. And if someone else comes along and wants to add another link or just a program, it will be refused. So you cannot step on each other. And this, like the BPF links had support in various other areas of the kernel where you can attach BPF, just not TC BPF. And the way TC BPF works, it didn't really fit to that BPF link model. So like the old style TC BPF, so you have those Q disks or like fake Q disks in the case of TC ingress, TC egress. So they don't actually do queuing. It's just like a hook to run something. And for those, like for this fake Q disk, you have filters where you can attach one or multiple filters, and inside the filters you have the CLS BPF, where you can attach one or more BPF programs. And all of this is managed through netlink in the kernel, and it doesn't really fit to the BPF link model. So basically, there had been some proposals on the kernel mailing list, but they got rejected, and so on and so forth. So basically, the idea was, given BPF links, they work really well with file descriptors, to go back, take a step back, and redesign the TC BPF data path for modern times. So basically, that you can attach and manage everything to the BPF system call. You don't have to go to netlink. You don't have to do all this QDisk and filter and classifier setup. You can just create a link. It's so very API driven. You can also have multiple programs that you can attach to that link, either links or programs directly, and you can also specify whether you want to attach something before or after, and so on and so forth. So I think, like in general, like for upstream, that's why it took quite a while. This API was the hardest to get everybody on the same board. It required a couple of rewrites, probably two or three times. I had to rewrite it to make everyone happy. But yeah, so now you have TCX, which supports BPF links. And the other nice benefit that comes on top of that, it's also like a new fast path for BPF. So you don't have to go into this QDisk filter and so on, like all the different layers of indirection in the kernel, which also eats up performance. You have like as fast as possible entry point from the stack. So like those two benefits. And then the other thing is this API, like this framework, which is called inside the kernel BPF mproc, so like multiproc. The idea here was to design it in a way that it can be reused in multiple different places. So one is for TCX as one user, but then the other one is, for example, netkit devices, and then the other one is cgroups BPF, maybe at some point XTP, and so on, so that you have the same look and feel when you manage programs throughout the different attachment points. So that's why like I had to work first on TCX, get that one merged, and then I could go back to netkit devices, because both ideas existed for around the same time, but like this was the prerequisite to then later on get netkit merged as well. Because if you would only be able to attach a single BPF program to netkit, it wouldn't fly upstream, because people want to have this multi-attachment possibility, right? Because that's just how the world works. You have different teams in an organization. They write different parts that they want to analyze. So like one is a policy or like security team, that has policy BPF programs. The other one is observability team, and so on. So that you can have this possibility, and you're not stuck with just one BPF program and then do the management on your own separately. So so we needed this multi-program attached to then also later to be able to merge netkit devices.
So does that mean netkit, you can only use netkit with these TCX attachment points?
Yeah, so actually when netkit is enabled in Cilium, so there's a data path mode where you can select Weave or netkit. When this is enabled, it will implicitly also enable TCX, because for all the physical devices that connect your traffic to the outside world, we attach things through TCX. And then for all the pods, we have netkit devices. So Cilium creates them and attaches everything through netkit. And the nice thing is, this is now unblocking that we can use BPF links for everything. So that is also what we achieved, like with Cilium 1.16, that we now have TCX, netkit, C group programs, and they all managed with BPF links, which is really nice because it makes the whole thing more robust, so that other software doesn't step on our toes and we not on others, right? So I think that's a really nice milestone that has been achieved with that as well.
That's great. So in my kind of mental model of attachment points in the network stack, I think of XTP, being like, as soon as that packet arrives, perhaps it's even being processed on the network card, and then the packet gets kind of put into a kernel data structure. I think it's the SKB structure. And at that point, that's where you start getting the TC attachment point. Where is TCX in that kind of continuum, if that is even the right model to think of it?
Yeah, I mean, TCX is basically in that TC layer. It is just executed before the old style TC construct, right? So yeah, it's in the same layer because, well, logically it makes sense because that's like the earliest point after TCP dump, where you can attach something in the receive path of the kernel. And the other nice benefit is that the SKB that the kernel creates is basically GRO aggregated. So whenever packets come into the node, there's like after XTP, there's the GRO engine, and the GRO engine tries to create like a super packet. For example, if you think of TCP data that is coming in, so typically that's coming in as a train of data, then it tries to aggregate up to a certain point. So 64K packets typically, and now it even goes further. So we have actually big TCP support in Cilium as well, so we can aggregate up to 192K to have even better performance. And then that big single packet is being pushed up the stack. And right after the GRO engine and after the TCP dump, if you have something attached there, comes TC/TCX. So it's basically the same layer. But it's super important because you operate on GRO aggregated packets, right? So oftentimes people say, oh, why not XTP? XTP is fast and so on, right? But if in the end packets actually end up in a local socket somewhere of that node, then I think SK buffs, they make sense because you get this aggregation.
Right, because otherwise you might end up with, I don't know, half a packet or half a layer 7 packet.
Yeah. And it's the same way on the way out. So the kernel creates SKBs like from the application, puts data in it, and creates those super packets and pushes them down the stack. So instead of n times or like MTU sized times, you only have to process it once.
Right.
So XTP is really good for load balancing, for DDoS protection, and so on, like for policy as early as possible. But later on, when traffic goes to local sockets in applications, I think it has like the TC and TCX has the nice benefit that you operate on aggregated data. I mean, like even like, I mean, it's quite a cost that you save. For example, compare, you have to do map lookups n times, and then in case of TCX, you only do it once because it has been aggregated.
So something, a light bulb has gone off in my head that I guess a netkit device probably doesn't actually have XDP, because
you've
taken that super packet and redirected it to the host device. I'm thinking of an outgoing from a pod packet, and it never had to be broken up into its smaller constituent L2 packets.
Yeah, I mean, it operates on SKBs. It doesn't have XDP support. One thing that I'm thinking further out in the future, what would be useful is potentially to have AF-XDP support, simply because now QEMO, it has an AF-XDP backend. So you could run lightweight VMs with AF-XDP as an input source. So I think for that, I'm quite open. It still requires some R&D and experimentation in terms of how can we make it fast. One thing I don't want to do is basically to do the same thing that has been done in terms of Weave devices, where they do have XDP support, but I think it's not fast enough. So like oftentimes I hear users complaining that, it's could be more efficient, in particular for 100 gigabit and beyond, like for those kind of workloads. So maybe there's a way where we can rethink that approach and do something better in general, which might be then supportable by various other virtual devices as well. So not just limited to netkit. So yeah, that's something I'm planning to look into like further out in the future.
All right. So before we move on, I want to in a moment talk about like the performance impact of this. But I just want to encourage the audience. I'm hoping this has all been making sense to you. But if you do have questions, or if anything was unclear, do type in a question and we'll try and help you out. And I think we have one other person who we didn't say hello to, but has said hello to us, which is Iban. So hi. Right. So I think we've got a picture of what netkit devices are. What is the impact of that in Cilium? What does it mean for a Cilium user?
Yeah. So in terms of performance, we did some measurements in our lab, which has some bare metal machines, 100 gigabit dual port NICs back to back. And we did some measurements around like traffic pushing from pod to another pod on different machine. And we tried to get as close as possible to 100 gigabit. So we did some tuning in the kernel. For example, I think we configured it with preempt none and various other things. And so this is where we get with 8K MTU. So it's not 9K, like 8K, so that it's tuned in a way where you get the most optimal GRO aggregation in the kernel. So it's tuned to a particular, so that you can aggregate exactly on the page boundary. Okay. And if you have if you run that benchmark from host to host, so not in a pod, then you get basically to 98 gigabit per second. That's the yellow bar that we had. And with a default Cilium configuration, which is not overly performant because it's trying to be the most compatible so that it can run in most environments without any hassles for users. What we got basically is 63 gigabit per second.
Right. And that's without Q proxy replacement, so still using lots of IP tables, I guess. Yeah.
I mean, the Q proxy replacement, like for this measurement, is not being utilized, right? So whether no services are configured basically, and if you don't have services configured, whether you use IP tables or whether it doesn't make too much of difference. But this is just really like to a pod IP. So no service IP, but to a pod IP.
Okay.
So then you get to the 63 gigabit per second, and there are a couple of problems here, right? Like in the stack, because the upper forwarding, it's like giving too early feedback to the TCP stack and so on. Like it's the way the kernel is designed, and it's like quite hard to change because it would break some compatibility, in this case around network to T proxy and so on. So that there are some details here in terms of why this is breaking the back pressure. If we use this so-called BPF host routing, this is with the helpers that I mentioned earlier, with this redirect peer, redirect neighbor, where you avoid going through the upper stack, but still have weave devices. You get to 89 gigabit per second. And then the purple bar is basically netkit in combination with that. So then if you exchange the weave devices to netkit, then you get really to the same numbers. So then you don't see overhead. And the same also in terms of latency. So here's another one with the latency for part to part, like for request response type workloads. So you also get to exactly the same latency number for P90, P99, and so on as we saw on the host itself. And what is also really cool, some developers, my colleague from Meta, he did some measurements for Meta production, where he replaced weave devices with an early prototype of netkit, when we wanted to see whether it also has visibility in terms of production traffic and making things better. And I hope you can see it. It's like probably hard to see, but this is a graph where he overlaid the CPU utilization for weave versus netkit, and the one on the top is basically weave. So like in case when there's pressure, you can see the spike, like in the middle, for example, in terms of soft IRQ, when the processing kicks in, where you have this double feedback loop, so it takes more overall more cycles to process higher load, and the bar on the bar below is basically the same workload with netkit, which is great. So yeah, it does have like visibility in terms of production traffic as well, which is awesome. I mean, it proves the point that we wanted to make.
Excellent. Yes. Yeah, it's good to have like proof that idea of something that it intuitively is going to be faster actually turns out in the real world to be faster. Yeah, great. Okay, so when will people be able to use this? This is 1.16, and 1.16 is coming out pretty soon, I think.
Yeah, it's coming out pretty soon. I think so today was actually the official date for the feature freeze for Cilium 1.16, and now it's a couple of weeks of stabilization and like solving the last release blockers, testing, and so on and so forth. So I think like probably around July is my expectation. There should be the next Cilium release. People can, of course, already test it, so there will be release candidates published. And you should be able to find them in the Slack channel or on the GitHub, where you can test and can help testing. And yeah, in terms of kernel, usually the assumption is, well, it takes like 5 years until someone can run it, but actually that's not the case. So the great thing is Canonical released Ubuntu 24.04, and that's their latest long-term stable, and you will be able to use all of this with Ubuntu 24.04, for example. So it's actually already out. It was released back in April, and yeah.
So 24.04 has like a 6.8.
I think it's 6.8. Yeah, I think it's 6.8.
Yeah, brilliant.
And yeah, so it was
And Nico
not
says
that
he's
long.
got it working in the lab. So yeah.
Very cool.
Awesome. The next thing will be getting it working in the isovalent.com/labs. But work for you, Nico. Great. Okay, so that's coming out soon. People are going to see this pretty significant benefit in networking performance. And then what? What's the next step?
Yeah, on the netkit kernel side, I have a couple of smaller improvements that I want to do. For example, some of the device parameters that we see, like for example, some users change things like their MTU and various other things at runtime. And today, the Cilium agent actually doesn't have access into the pod. Like I was figuring, I mean, maybe we should also solve that problem because it can be a hassle from time to time. So my next step for netkit is to make some small improvements where you can basically configure all these parameters from the primary device, so that Cilium only has to change the MTU from the primary device, and it will automatically adapt the one inside the peer device. And there are also a couple of other things I plan to look into. Some of the device parameters in the kernel, they tell how much headroom and how much tail room to reserve on the packet. And when you use things like encapsulation or even encryption like WireGuard, they need a bit of tail room in order to add like something to the end of the packet. And so this should improve the performance slightly improve it as well. So that's my plan from the netkit kernel side. But then the bigger one, as I mentioned, would be to be able to support AFXDP. I think that would be huge. And especially to make it fast. I mean, if it's otherwise, there would be no point to do that. Yeah, and right now, like still before the release, I've been looking into big TCP. That's what I'm currently looking into, because it looks like there has been a regression in the kernel. So big TCP, for those who don't know it, I think that's also a really fascinating idea. Very simple idea, but it has tremendous effect. And that's basically to get to much bigger aggregation in terms of GAO and GSO, to get to up to 192K instead of 64, right? So to go beyond that limit. And this also this can be used together with netkit as well. And yeah, so there has been a regression in the kernel. So that's my next step to look into and to send a fix for that. But I think, yeah, like after those things, like in particular AFXDP, I think should be in a really good state. There are plans outside of netkit that we're looking into, in particular around WireGuard, and to make WireGuard in the kernel faster. So I think that this will be an exciting project. And super useful we see more and more users adopting Cilium with WireGuard, and then it would be like a perfect combination so that you can have things like netkit, big TCP, and WireGuard. I think this would be amazing. So yeah.
Awesome. So beforehand, we collected together lots of links about netkit, and they're in the show notes, again, available on HackMD. A couple of things I'll point out. There's the talk that Daniel did about netkit at, I guess that was Paris KubeCon.
Yeah, that's correct.
Yeah.
Yeah.
Documentation about configuring netkit on Cilium, and I will mention that when I said that Nico would be putting it into isovalent.com/labs, apparently that is the plan. So coming soon to a lab near you. There's quite a few other articles and even some pointers to the kernel code in here. So if you're watching and you want to dig into the details, you'll basically find all the resources in those show notes.
And at this point, I also wanted to give a shout out to folks from Datadog and ByteDance, because they helped as well to get it supported for the Netlink Go library, for the Cilium eBPF library, and so on. So it was really awesome to see that there's a big community interest and support as well for that.
Yeah, fantastic. So thank you to those folks who were involved in that. Brilliant. If you're watching and you've got any last minute questions, you'll need to type really fast. We're getting pretty much to the end of the hour anyway, and I think we've covered, unless you've got anything else you wanted to add, Daniel.
I mean, maybe just one last point. So we updated the Cilium documentation. There's this tuning guide where you can see the various options to improve the performance of Cilium, and then there's also, we now also have a recommendation section where we give an example in terms of how to configure all these things together. So basically, there's eBPF host routing, netkit, and big TCP, so that users have an easier way to find it and see what is relevant or like most relevant in terms of performance, and can try it out themselves.
Fantastic. Ganu's hack mentioning that the HackMD that we put together is handy. So thank you for that feedback. That's great. Good to know. And yeah, I think with that, I'm just going to say thank you so much. Oh, Tony's saying this is one for his home lab. It's going to be a very high performance home lab. Awesome. With that, Daniel, thank you so much for your time and expertise, and for sharing, well, and also for the work that's going into making Cilium even more performant. So fantastic.
Yeah, it was fun, definitely.
Excellent. So for everyone else, I'm going to be away next week, but eCHO will be here as always. I think it's Duffy up next week. And yeah, have a great weekend, everyone. Bye.
Thanks for having me. Bye.